Welcome to studying functional programming. So the Lambda Calculus. Yeah, I'll just get into this. So the Lambda Calculus has a number of properties which suited well for describing programming languages. First of all, abstraction and application are all that are needed to develop representations for arbitrary programming language constructs. So what does this really mean, right? It's funny, like I've been kind of on and off, studying functional programming for well, I guess for 10 years or so. And it's kind of, I've reread these kinds of lines, many times. And somehow the context always expands. So when you say abstraction and application, that's about it, right? No, I will not now get philosophical with this. That's actually one thing that may happen. Like when you study this and you end up, making big rabbit holes and thinking about it. So let's move on. So Lambda Calculus can be treated as a universal machine code for programming languages. So in one sense, Lambda Calculus is like an assembly code. But it's a different kind of assembly code, right? It's the one assembly code where the unit itself, it's a function. So it's kind of a different viewpoint. I think the problem would be trying to understand it from one's own viewpoint, which may be actually also beneficial, but a universal machine code, but it's somehow independent of the underlying machine, because you're just thinking of functions. But what does that mean? You're thinking of relations independently of what kind of, values you put them in the function. And since the functions themselves are pure, but that's the tricky part, right? Why are they pure? But they're pure by default, right? They're pure by default. It's not like they are impure and pure and these ones are pure. But I guess the way they say they are pure is basically an extra explanation, because they are pure by default. If you look at well, let's move on. In particular, because the Lambda Calculus is evaluation order independent, it can be used to describe and investigate the implications of different evaluation orders in different programming languages. Now that's a mouthful. But because the Lambda Calculus is evaluation or order independent, but what does that even mean? Well, I guess this has to do with equational reasoning, right? Because if the functions are pure, well, I guess you could say if I add four numbers, 1, 2, 3, and 4, there are many ways, right? Let's go to let's say I have 2 plus 3 plus 4. Well, it's 9, but I could do it like 2 plus 7, right? It's still 9. Or I could do it like 5 plus 4. It's still 9, right? So evaluation, well, I guess you could go deep really and say this is not the same thing. But at the end we get the same result. So in that sense, um, implications of different evaluation orders. So because the lambda calculus is evaluation order independent, well, I guess it can be used to describe and investigate the implications of different evaluations. Furthermore, there are well-developed proof techniques for the lambda calculus, and these can be applied to lambda calculus language descriptions of other languages. Sorry, I'm a bit sick, so hence me with my nose. Finally, because the lambda calculus is very simple, it is relatively easy to implement. Thus, a lambda calculus description of language can be used as a prototype, a run on a lambda calculus implementation to try the language out. Summary of the rest of the book. So this book is from Greg Michaelson. I will put the link into the description. So lately I've been doing OCaml, right? And OCaml somehow has brought me to standard ML, which is a wonderful language. I'm actually quite surprised because all of these things were written like 20 or more years ago. But the course actually, do I have it already opened? ML equivalence, yeah. So the principles of functional programming is one of the introductory computer science courses for the undergraduate in the School of Computer Science at Carnegie Mellon. Carnegie Mellon is kind of known by ML, I think, because Robert Harper works there, as well as, I guess, some of the other ML people. And it's kind of a very nice language. I'm very surprised it didn't take off more than it did, I guess. And I think it's really great to start with it. I think it's great to start, actually, I think it's great, of course, to start with lambda calculus. So it's, in some sense, I'm going now again, back, and to start with lambda calculus, and then learn something like standard ML, and maybe then progress to Haskell with call by need. Because call by need, or how should I say it? Maybe to build up more appreciation for call by need, but because call by need, or the lazy evaluation, right, provides to me, then that might be my very naive observation, a rich field for, when I say field, I just mean like ground, for abstraction, because, right, you can put away the values that you maybe do not want to compute right now, and call by value is, I guess, well, you have to evaluate the entire evaluation. And I think, and I might be saying this wrong, but SML, well, in call by value, you evaluate the arguments, and then I think you go from inside to outside. And in call by need, you evaluate arguments as you need them, right? So it's almost like you can, well, I will not go into it now. I shouldn't go too deep now into explaining these things in bad ways, but there is a difference, and I think I think it's really nice to start with something like SML and scheme, and then maybe progress. Just as in all of these lectures, they actually introduce lazy evaluation much later in the lecture, which somehow, so it's important to build up some kind of appreciation for something like that, rather than immediately beginning, with Haskell. And maybe, maybe that kind of helps to build up more resilience and more understanding and appreciation. So when, tough times come, you can go through them. When I mean tough times, why functional? Yeah, so there are a couple of really nice lectures and ML books. That's really nice. So Greg actually wrote a book on ML, elementary ML, and this is Dan Grossman also. He's really nice. So anyway, I've been doing all of this, but what's actually most important to really get this appreciation, of course, for all of this is to do Lambda Calculus. And in a lot of the books, this is really not so covered, or sometimes there's only one chapter about it. And you kind of learn what's the application, what's the abstraction, and maybe there are a couple of examples, or maybe there are too complex examples where you have to manipulate, But Greg wrote a book about this. And later in the book, he kind of introduces ML and also Lisp. So I think it would be really cool to go through this book, and I'm kind of started to read it, but I also want to record myself while doing the book, because I think it will help me to, process my thoughts and kind of get the most out of the book. And basically, this is the way how I work. So I kind of was thought like, what am I going to stream? I have to have some kind of a project, But this is how I work. So how I have fun. So in this book, we're going to use Lambda Calculus to explore functional programming. Pure Lambda Calculus does not look much like a programming language. Indeed, all it provides are names, right? So you gotta have a name. That's the great thing about the Lambda Calculus, right? You have all the functions, right? But what do you need? You need to have a way how to name them. But that's like the basic thing. Is like we have a bunch of people. Well, after a while, you might not need names, right? I don't know if like cats have names for themselves. Maybe they don't need names. Maybe they have smells instead of names. What's a name, right? We can't smell all other people. We could smell them, but I guess we use the best abstraction that we can. So you need names after a while. So it provides names and function abstraction. So the way how do you combine the functions, right? And again, this term, it's about relations, not so much about changing values. And so it's about more like transformation and interdependence, right? And that's what I really love about, functional programming, because it somehow thinks about the rest. It's not just about the head, but it's about the rest. Okay, so all it provides are names, function abstraction, and what else do you need? Function application. So you have to do something, right? So we have names, we have function abstraction, right? In the sense of how to combine our expressions. And we have function application, how to apply it. So how to make new expressions out of, well, you see, I guess you could mix these two up, abstraction and application. Wait. Is this too loud? Maybe. Right. Encoding overloaded. Maybe I don't need the quality. I will put it less. Like this, maybe. Right. Put this one. Yeah, I'll just put some music because why not? Sorry about that. Yeah, all right. Encoding overloaded. Let's see. Come on, come on, come on, come on, come on. Let me just check actually settings. Output 6000. Yeah, very fast. All right. Chapter 2, we will look at pure lambda calculus. So first we're going to do it so without types, right? Untyped. Yes, and the thing about types is, I guess you naturally come to the idea of types, right? So you have like a bunch of functions, and after a while you have names, all right? You have some means to combine them, right? But after a while you have to make some kind of structure, and this is where types come. They come on their own. Examine, so let's say you have certain kinds of numbers, so that's a type of a number, right? And then you have certain types of operations, so you make that into a type. And develop functions for representing pairs of objects. Oh, pairs of objects, I guess tuples. These will be used as building blocks in subsequent chapters. We will also introduce simplified notations for lambda expressions and for function definitions. In chapter 3, we will develop representations for Boolean values and operations, nice, numbers and conditional expressions. Chapter 4, we will develop representations for recursive functions. And also the way, because recursive, and use them to construct arithmetic operations. It's like there is no idea of a loop where you have, functions. The idea of a loop only exists when you constantly change one value. But if all you have are functions and you need to repeat something, of course you will call functions to do the same thing. So the recursive aspect is actually, natural. And we all do it in real life. I was trying to find something, to compare it to, but yeah, I guess we'll get back to this. In chapter 5, we will discuss types and introduce typed representations for Boolean values, numbers, and characters. We will also introduce notations for case definitions of functions. In chapter 6, we will develop representation for lists and look at linear list processing. 7, we will extend linear list processing techniques to composite values and look at nested structures like trees. Isn't this great? And this book is old. In chapter 8, we will discuss different evaluation orders and termination. Chapter 9, we will look at functional programming in standard ML, using the techniques developed in earlier chapters. And standard ML is quite nice. I'm so surprised. In chapter 10, we will look at functional programming in Lisp using the techniques. Okay, notations, programs, Greek letters, okay, alpha, beta, lambda, eta, syntactic constructs, BNF rules. Each rule has a rule name consisting of one or more words within angle brackets. A rule, so that's a rule, I guess, associates its name with a rule body consisting of a sequence of symbols and rule names. If there are different possible rule bodies for the same rule, they are separated by S, digit, binary number, can be either a single digit or a digit followed by a number. So what's a binary? Look at this. Either, yeah. It's nice, when you look at this, I was first confused with this, but is it this and this? Well, it can be either this or this. It's almost like a description of what this means, not actually what it is. I guess what could be, you know. Anyway, in this chapter we have discussed the differences between imperative and functional programming. So this first actually chapter is kind of, it's not long, but I didn't really read it whole. But it's very interesting, and he takes great care. Greg takes great care actually when he, and it's, for me it's very helpful, but it's also nice how he goes slow with this. And as I said, one of the most important things I find is to build a appreciation. So to go really slow through it and really, you know, cover everything. You build really strength and resilience when you tackle more, you know, difficult things in the future. And since in a way, whatever you learn in functional programming somehow builds upon itself. So if you learn well something like Lambda Calculus, it really builds on itself. But I guess it all depends. I'm not trying to preach here, you know. It's just, I guess, something what I find very nice. You know, I really love actually learning all of these things. That's the most fun. That's the most fun thing, right? Well, the most fun thing. I mean, anyway. Imperative languages are based on assignment sequences, whereas functional languages are based on nested function calls. Right. So I guess these are actually different ways how you program. Yeah, okay. In imperative languages, the same name may be associated with several values, right? That makes sense. Whereas in functional languages, a name is only associated with one value, because you transform it again through function calls, not by updating the name with a new value. It's like you have a list of things to buy, right? And you want to cross some and stuff like that. So each time you want to cross or add, you make a new list. So that way you keep all the lists that you change. So in some sense, you keep a version control of all the lists you made. Imperative languages have fixed evaluation orders, right? Because evaluation matters, whereas functional languages need not, right? Because it's functional. Okay, I'll stop. In imperative languages, new values may be associated with the same name through command repetition, whereas in functional languages, new names are associated with new values through recursive function call nesting. So this is the same actually what he said before, but it's kind of a different way, which helps. Functional languages provide explicit data structure representations, right? Because through each function call, you kind of somehow explicitly represent the data structure, because you copy it and you update it with new values. So in that sense is explicit. Functions are values, okay? And he talked a bit about the history and such. Lambda Calculus introduction. We're going to meet the Lambda Calculus. I also have I have this actually. I'm going into the church mode. When I say church mode, I mean Alonzo Church. You know, I thought I will need more pen, you know, and then I will write Lambda Calculus with my pen. Although I found something like this actually, right? This is cool. Next step 2, look at this. So you have also stuff online, right? Lambda x.x. Can we do like a print something? Hello? Yeah, next step. And we got a hello. This is the identity function. Can you name things here? Identity. No. Identity. x dot x. Yeah, term is not. Yeah, okay. Okay. So to begin with, we will briefly discuss abstraction as a generalization through the introduction of names in expressions and specialization through the replacement of names with values. So, abstraction as generalization through the introduction of names in expressions. Abstraction, right, and specialization through the replacement of names with values. We will also consider the role of abstraction in programming languages. Abstraction, right. So it's like what I showed before here. Let's say you have 3 plus 3 times, let's do 1 plus 2 times 3, right? Let's do it even bigger. 1 plus 2 times 3, right? So, and then we have 2 plus 2, for example, times 3. That's 8. But let's say you want to make an abstraction of sorts, and you see if I do 3 plus 2 times 3. Yeah, you might say, why would I do this? I don't know, you know, but abstraction itself would be to look at what changes and what does not change. 1 plus 2 times 3. That's the how actually in Haskell book. Haskell programming from first principles. So in that book actually it has a first chapter is about Lambda Calculus, but it's kind of too brief for my taste. And it's too brief because you can't just write half of the book about that. But in the next chapter it begins somehow also, like each book somehow represents abstraction in some way, which is kind of cool. And but in that book they were saying, I remember the line, like what changes and what stays the same, right? So he was trying to describe some kind of principle of abstraction. So like in this case, this times 3 does not change, n plus 2 actually does not change, but 1, 2, and 3 did change, right? So then we could, how do we write that? And each time, that was written in the ML book. The problem with this is because each time you have to copy the entire thing. It's like when you use a calculator, right? You always have to retype. So let's say I do 4 plus and I have to retype. I have to retype the same thing, right? And we're kind of used to that. But abstraction is me saying, okay, let's do 5 plus, and no, let's do actually turn this into a variable, right? Because it will change. And then this actually I copy out, right? Maybe this does not make sense now, x plus 2 times 3, but that's the idea, because the x is always changing. So whatever is changing, you put into a variable. Why? Because, yeah, that's a good question. But look at this. So val my function, I'll just call it my fun, equals val my fun equals, well, I don't know ML yet really, but x plus 2 times 3. Interesting. Well, let's start actually with something simple. Let's start with 1 plus 1. Okay. And then 2 plus 1. No, 2 plus 1. And then 3 plus 1. So 1 stays the same and 1, 2, 3 was changing. So this would mean that it's some kind of x plus 1, right? So how do I do that? X plus 1. So val this will be called an increment function actually. That's an yes, increment x, I guess. Increment x. Increment of some number equals that number plus 1. Will this work? Unbound constructor x. Val increment x. Unbound variable or constructor x. Val increment x. Yeah, this is me not knowing actually how to use SML. What would be, because we have a, because in Haskell we could be also increment x equals x plus 1 unbound. So val, does it have like let val? No, forgot, horrible. I want to show a simple increment function in standard ML. Fun increment, val result increment, with value store, okay. With val you give a name. That was the mistake. With val you give a name, val x, so it's like you have a value of sorts, 5, right? Val and 5, so val x equals 5. And now you have, when I check the name, it's 5, right? So I was actually trying to define a function, which would mean fun. I mean fun increment, fun inc x. Oh, he's declaring a type here. Okay, fun inc x is a type of an int, and the function itself produces an int. I guess that's what that means. So fun inc, yeah, this looks way more complicated actually. I guess I wouldn't need it. Equals x plus 1. So now I have inc1 is 2. Can I define it without the type declaration? I think I can. Fun inc x equals x plus 1. Yes. So inc1 is 2. But because I didn't declare a type, I think I have to. Yeah, I think I'll get back to the book. But anyway, you see the point. I see the point. Okay, let's see this. Attribution notation. Oh, okay, he's just describing what will all happen. Abstraction, right. Okay, now he starts here actually. So I'm kind of doing actually ML and Lambda Calculus at the same time. And he also has this really nice book, Greg Michaelson, Elements of ML. Elements of ML. It's also free. Look at this, elementary standard ML. Isn't that great? Let's actually download it. Standard ML. So look at this book. This is really nice. Elementary. So 2002. Where to start functional programming. And he's really, look at this, he's really nice. Checking names, and it's really nice. Basic types, goes into types, tuples, everything. I think, you know, I'm sure, like, when I look at all this, and that would be really nice to learn standard ML and to maybe do advent of code or 99, 99 set of problems in standard ML. Look, folding lists of lists, generalized folding, tuple lists, text processing, data types, new types, defining lists and trees. Isn't that cool? There are so many books, actually. They're really good. Prologue. Between thought and expression, there lies a lifetime. Lou Reed. Look at this. This book is intended to support a first-level course in programming in standard ML, SML. No previous programming experience is required. No mathematical abilities required beyond competence. So this is also cool. I will be doing this also. Okay, let's back to our... So abstraction is central to problem solving and programming. Yeah, it's something, sometimes they always represent programming as problem solving. It's like everything has to be a problem, but maybe that's just me seeing it in a negative light. Okay. It involves generalization from concrete instances of a problem to that a general solution may be formulated. Yeah, like we did now with the ×3 and with the with this, right? With the increment function. A general abstract solution may then be used in turn to solve particular concrete instances of the problem. The simplest way to specify an instance of a problem is in terms of particular concrete operations. On particular concrete objects, abstraction is based on the use of names to stand for concrete objects and operations to generalize the instances. A generalized instance may subsequently be turned into a particular instance by replacing the names with new concrete objects and operations. Oh, horrible. We will try to get a feel for abstraction through a somewhat contrived example. Consider buying 9 items and 10 pence each. The total cost is... I'm sorry for that, really. Was that too loud? Wait, now it's better. I think my sound here was too high. Okay, now? Yeah. Oh, I think my son put this. Yeah, that's why it was so loud. So we will try to get a feel for abstraction through a somewhat contrived example. Consider buying 9 items at 10 pence each. Yeah, okay, that's a similar example. The total cost is 10 times 9. Here we are carrying out the concrete operation of multiplication of the concrete values 10 and 9. Now consider buying 11 items at 10 pence each. The total cost is 10 times 11. Okay, in the previous examples I kept this, the last, actually, yeah, okay. Here we are carrying out the concrete operation of multiplication of the concrete values 10 and 11. We can see that the number of items changes. So, right. So that's the price. 9 items at 10 pence. Okay, I guess you could say, dollars. $10. What's pence? Is it like a UK expression or something? Pence. Like pennies? Okay, 10 cents. 10 cents and 9 of something. Carrying out concrete, now 10 cents and 11 items. here we are carrying out concrete operation of multiplication. We can see that the number of items changes. So the formula for the total cost changes at the place where the number of items appear. We can abstract over the number of items in the formula by introducing a name to stand for a general number of items. Say items, 10 times items. We might make this abstraction explicit by preceding the formula with the name used for abstraction. Replace items in 10 items. Oh, so he's saying like 10 items. 10. So let's say we have 9 items times, well, the price is 10. The price is 10 times, and this is actually not, so it's like 9 items. Items of, what would be the thing that you buy like 9? And that you pay, it's sometimes these examples have to be practical, like you don't buy 9 shoes, right? Maybe 9. What else do you, but 9? I don't know. 9 books, but books don't have a fixed price. 9. What does have a fixed price? Because everything sells in a box or something. If it's more than 4 or 5, yeah, okay. Anyway, you see the big problem. 10 times 9, right? That's 90. And then 10 times 10, that's 100. So it's 10 times some number of items, right? But the thing is, we don't have this some number of items. How do we, right? Right. That's what we did before with val x, with val items. But val items is what? You could say 10, right? And now if you do items, you get 10. And now you can do 10 times items. And you get 100. Sorry. But he's introducing here a replace function. We might make this abstraction explicit by preceding the formula with the name used for abstraction. Replace items in 10 times items. Here we have abstracted over an operand in the formula. To evaluate this abstraction, we need to supply a value for the name. For example, for 84 items. Replace items with 84 in 10 times items. I guess he's not showing us how to program this, but maybe to understand it. Okay, so 10 items. This is kind of way to think through it. So 10 times some number of items. But he says here to make this abstraction explicit. Well, you might say, isn't it explicit now because it's named items? But preceding the formula with the name used for abstraction, replace items in 10 times items. So that you can update it. Yeah. We have abstracted over an operand. So the operator is the function, right? It's times, and operand is the items. To evaluate this abstraction, we need to supply a value for the name. For example, for 84 items, replace items. Yeah, which gives 10 times 84. We have made a function from a formula by replacing an object with a name and identifying the name that we used. We have then evaluated the function by replacing the name in the formula with a new object and evaluating the resulting formula. Let us use abstraction again to generalize our example further. Suppose the cost of items goes up to 11 pence. Now the total cost of items, well, what if the price will rise, right? Replace items in 11 times items. Suppose the cost of items drops to 9 pence. Now the total cost of items is replace items in 9 times items. So now we need to introduce some kind of abstraction here that will encapsulate the price. Because the cost, the price or the cost, because the cost changes, we could also introduce a name to stand for the cost in general. Say cost. Replace cost in replace items in cost times items. Yeah. I guess you could use this with AB. Replace cost. It's like let A in, let B in A plus B. Here we have abstracted over, and outside you can give the, yeah, I'm not sure how you write this, but this would be a nice way how to show this. Wait a second, wait a second, wait a second, wait a second. I'm onto something. I'm onto something. It's okay. Let's use this example to, I think you can show in SML a lambda expression. Something like let A in let B in A plus B, and outside provide the values for A and B. Lambda expression for computing total cost. Val compute total. Cost times items. So right, let's just try this for fun. So we have a val compute. So val compute total. We don't need the total. Val total. Wait. Remove compute total and just leave total. Oh, he has a let also. Oh, that was an intermediary binding. Wait. I shouldn't skip the total val result. Okay, let's actually do what he did here and see. Val compute total. Compute total. So what do we have? Okay, this is just the way how you write lambda expressions. Fn cost. Oh, Fn is the way how you name functions. So we have a function. Maybe let's go into the second line so that you can see this. Fn cost, and now we are going to introduce a lambda function, right? Fn items. Fn items is cost times items, right? So now we have a compute total function. It's a function that takes an int to an int, and as a result produces an int. Cost times items is some kind of a result. And now provide values for cost and items. Let's see this. Val result is what? It's compute total. Now we're going to give values. Compute total. Let's do 9. So 10 is the price. Okay, and 9 is the number of things we're buying. Compute total 10 and 9. Oh, this is actually just a comment. So the cost is 10 and the items is 9. He's introducing 5. Right, that's the result. And print the result, val. So we have here actually a placeholder. Interesting. Print. The total cost is. The total cost is. We have now a caret symbol. That's how you. Yeah, that's how you combine strings. Now he's using toString function, I guess, to turn a number into a string. Result, yeah, and combine that. Okay, we didn't learn this, but maybe it makes sense. Unclosed string. Yeah, there was something wrong here. Yeah, well, that means I don't know enough. Here we have abstracted over 2 operands. To evaluate the abstraction, we need to supply 2 values, right? So for example, 12 items at 32 pence will have total cost. Replace cost with 32 in replace items with 12 in cost times items. But do you see here we have a replace function that is called twice, right? Replace cost with this value in what? Replace items with 12, and then so we have one function call, second function call, and the third function call in what? Cost times items. We have 3 function calls here. So for example, 25 items at 15 pence will have total cost, replace cost with 15, in replace items with 25 in cost times items, which is replace items with 25 in 15 times items, which is 15 times 25. Suppose we want to solve a different problem. We are given the total cost and the number of items, and we want to find out. So it's interesting, it is a book now about Lambda Calculus, and this is how he starts it. So we're given the total cost and the number of items. We want to find out how much each item costs. So for example, if 12 items cost 144 pence, then each item costs 144 divided by 12. Yeah. So we have a total cost which is 144, and we are curious about how much each item costs if we have 12 of them. So if 15 items cost 45 pence, then each item costs 45 divided by 12. 15 items costs 45 pence. Okay, then each of them costs 45 divided by 12. Okay, in general, if items cost pence, then each item costs. Replace cost in replace items in cost divided by items. Yeah, now compare this with the formula for finding a total cost. Replace cost in replace items in cost times items. Interesting. They are the same except for the operation divided in finding the cost for each item. But how would this look like in finding the cost of all items? We have 2 instances of a problem involving applying an operation to 2 operands. We could generalize these instances by introducing a name, say op, where the operation is used. Wow, this is very interesting how he does this. So let's do this in SML. So we're given the total cost and the number of items. We want to find out how much each item costs. in the number of items. And we want to find out how much each item costs. If 12 items cost 144 pence, right? If I have 12 things, and they cost $144, that means that 144 divided by 12. Operator and operand do not agree. Overload. Real and real. Oh yeah, that's the hack. So you cannot use, I think that's same, camel. Yeah. You cannot use, I think I wanted to do just integer division. No, that's a real division. Well, 12 times 12 is 144. Is it 144 div 12? It's div. Alright, I'll use div. And I think 144 this 12 operator is not a function. What, like 144, let's see this 144 dot 0 like this. No, operator is not a function. 4 times 0, let's try like this. No. Okay, I'll stay with 4 div 12. So the price of each item is 12 if I have them 12. So if 15 items costs 45 pence, then each item costs, but wait a second, now we have 15 items costs 45 pence. I guess he's trying to, I don't know what, so we have 15 items now. And they cost 45 pence. So that means 45, it's the total, divided by 15. We get 3. Why did he change? 12 items costs 144. And 15 items costs 45 pence. Then each item costs. So it's, I guess there are 2 examples. In general, if items cost, it's weird to read this actually. It would be nice if it was, then each item costs. Replace cost in, replace items in, cost items. Yeah, how would we represent this? Let's do copy this. Curious. We can represent the concept of replacing variables, cost, and items with values in a scoped way using lambda expressions or let expressions. Using nested let. I guess you could use, yeah. You can use let. Maybe lambda is too confusing now. Yeah, this is too confusing. Let's use this with let, and can we just output the result without using the val and print and such? Simply write the computation and rely on the interpreter. Yeah, here's how you can do it using let. So what do we have? Let val cost. So what's the cost? He said 45 is the cost. 45 is the cost, right? Is the cost. 45, but do we put a 0 actually? Let's try this. Let val cost is 45. In what? In, let's do like this, let val items, right? Now we're going to declare items. We have them 15, right? 15. In what? In cost times cost actually divided by items. We have to write an and here for this. And. So this is actually very simple. And it's 3. 45 divided by 15 is 3. Maybe it would be, maybe show this. Yes, let's do it like, let val A equals 3. Let val A equals 3 and let val B equals 2. Let's do something. Let val A equals 3 and let val B equals 2 in a, well, let's call it back here actually. This would be cool. Wait. How do I? How do I stop it? Look at this. Okay. Syntax error. Look, wait. Let val A equals 3 and let B equals A times A. Right? And let B equals A times A. In A plus B. Syntax error. Yeah, you see what I want to do? I want to do let val A equals 3 in let B equals let val B equals A times A in A plus B. And this should work. 12. So you see what we did here. A is 3 and B is A times. So we called A inside the scope. A is 3, B is A times A, 3 times 3 is B. In what? A, 3 plus 9. So 3 plus 9 is 12. All right, I guess that's what he's trying to do here actually with cost. Replace cost and replace items and cost divided by items. Now compare this with the formula for finding a total cost. Replace cost and replace items and cost times items. And he's reusing it. I think he's trying to also teach these recursive calls. They are the same except for the operation divide or div in finding the cost of each item and in finding the cost of all items. We have two instances of a problem involving applying an operation to two operands. We could generalize these instances by introducing a name, say op, where the operation is used. Well, he's now abstracting over something. What is he abstracting? They're the same except for the operation div in finding the cost of each item. Oh, and multiplication. So we're kind of, yes, let's say we could save this into some kind of a function, but here we are making a, okay, this AB was just an example. But here we did cost divided by items, and what if we want to cost times items? That's what he's trying to now abstract over. So now he's not just abstracting over values, he's abstracting over some kind of operation. which is cost times items or cost divided by items. So we have two instances of a problem involving applying an operation to two operands. In one, we apply an operation of multiplication, and the other, we apply an operation of division. We could generalize these instances. Now we come to the abstraction. We could generalize these instances by introducing a name, say op, where the operation is used. Replace op and replace cost and replace items and cost op items. So now he abstracted over the operation itself. But it's interesting. How would we do this in SML? How would we replace the times? But how would we actually abstract over an operation? So let's say we want to be able to do cost divided by items and also cost times items. So an example is this. To abstract over an operation like plus, we can define a higher order function. He's introducing higher order functions so soon that takes the operation as a parameter in standard ML. So we would have to have a function that takes a parameter. This is now a higher order function. Wow. Right? So you're not just you are abstracting over an operation to have an operation that you say, okay, what kind of a function do you want? Well, takes the operation op as a parameter in standard ML. Abstracting over an operation with let val op fn x of y x divided by y. Replace this with any operation, x times y. Oh. Making it more flexible with a function. If you want to reuse this logic with different operations, you can define a function that takes op, cost, and items as arguments. Function compute. Op is a function from a real to a real, from a real times real. This is, I think, a type constructor. I think this is too advanced for me to now talk about this. This is a type constructor, real times real. I think this is how they do it in ML. Cost is real, items is real, and the whole function is real. I think this is op, cost, items. So this is an entire abstraction, right? The op and cost items as a tuple. So val result 1 is compute fn xy, x divided by y, and you provide 20 and 5, and you divide them like that, right? And result 2, compute fn xy, and oh, this is interesting. ML is really cool, but I think this is too much for now, actually. I think that's not the point what he's trying. He's just trying to make some kind of a mental follow, right? Now that's why he's not actually, this is more like a pseudocode. Now finding the total cost will require the replacement of the operation name with the concrete multiplication operation. So replace op with multiplication in what? In replace cost, and replace items in cost op items. So he's almost training us to do this function substitution and calling function nested calling, right? Because the functions are nested and they are calling. Function call, which is, I guess you can use call or application. But maybe that's different because functions call themselves and they apply themselves. I don't know. Which is replace cost in replace items in cost times items. Similarly, finding the cost of each item will require the replacement of the operation name with the concrete division operation. Replace op with, now he's showing an example with division. So replace op, and op can be either multiplication or division. So now, example with division. Replace op, which is a name for our function. Replace op with division, right here. Wait, I don't have. Replace op with division in replace cost and replace item in cost op items, which is replace cost and replace items in cost divided now by items. So right, so abstraction is based on generalization through the introduction of a name to replace a value, and specialization through the replacement of a name with another value. That's what he means by special. I was confused at first, I didn't know what he really means by, what he meant by specialization. Through the replacement of a name with another value. Oh, specialization is when we do have a name and provided a different value. So it's almost like we are specializing. So the variable itself specializes. Wait, did I video paused? Why? It's like Tron. Programs. The grid. Abstraction based on generalization. Yeah, I think it would be nice to have what's his name? Wait a second. The dude. The dude. The Big Lebowski, not the Big Lebowski, the Jeff Bridges. Wait a second, I have to do Jeff Bridges AI voice. My nose. AI text. Jeff Bridges. Get started for free. Yeah, these things are really bad. Jeff Bridges. Jeff Bridges, laid back, trustworthy storyteller. De-aged. Jeff Bridges. Too bad. The grid. Yeah, it was so nice. It would be nice if I could use Jeff to read me this book with the Tron, you know, background, with the soundtrack. I think we would learn much better. It's like, we're like, oh yeah. And then they show lights, like, you know, function calls, and, you know, lambdas, and you can touch them like this, you know. That'd be nice. Abstraction is based, okay, it's based, wait, so note that care must be taken with generalization and replacement to ensure that names are replaced by objects of appropriate types. For example, in the above example, the operand names must be replaced by numbers, and the operator name must be replaced by an operation. with two number arguments. Okay, right? So you cannot provide something else like a burger. Abstraction in programming languages. Abstraction lies at the heart of all programming languages. In imperative languages, variables as name, value, associations are abstractions for computer memory locations based on specific address value association. So that's the thing, yeah. It's like, it was always weird for me in the imperative languages. I mean, I get the memory. It's not like you don't care about the memory, but it's like the way I think is defined by memory locations. I don't know. It's just something, I guess it's something to think about, you know. The particular address for a variable is irrelevant so long as the name value association is consistent. Indeed, on a computer with memory management, a variable will correspond to many different concrete locations as a program's data space is swapped in, out, and of different physical memory areas. The compiler and the runtime system make sure that variables are implemented as consistent concrete locations. Where there are abstractions, there are mechanisms for introducing them and for specializing them. For example, in Pascal, variables are introduced with declarations and given values by statements for use in subsequent statements. Variables are then used as abstractions for memory addresses on the left of assignment statements or in read statements, and as abstractions for values and expressions on the right of assignment statements or in write statements. Abstractions may be subject to further abstractions, right? That's what we want. This is the basis of hierarchical program design methodologies and modularity. For example, Pascal procedures are abstractions for sequences of statements, yes, named by procedure declarations. And functions are abstractions for expressions, named by function declarations. Procedures and functions declare formal parameters which identify the names used to abstract in statement sequences and expressions. I guess all of this might sound complicated, but you have to read it a lot until you just understand it. But what's different here is functions declare formal parameters, and then the arguments are provided to the parameters, right? So let's see which identify the names used to abstract in statement sequences and expressions. Simple array and record variable formal parameters are abstractions for simple array and record variables in statements and expressions. Procedure and function formal parameters are abstractions for procedures and functions in statements and expressions. Actual parameters specialize procedures and functions. Procedure calls with actual parameters invoke sequences of statements with formal parameters replaced by actual parameters. Similarly, function calls with actual parameters evaluate expressions with formal parameters replaced by actual parameters. There's kind of a lot of words here, which I appreciate, but it's interesting how different they sound than something like in a Haskell book. This would be written actually differently. So a good way how to use ChatGPT is, look at this, summarize or extract the essence of this. The essence of this passage is: abstractions can be layered and are central to modular and hierarchical program design. Procedures abstract sequences of statements. Functions abstract expressions. Okay. Because I guess procedures, no one uses that, now. So like no one uses the term procedures lately, like in recent years, right? Written 20 years ago or so, when this term was more used. Can you reframe the passage into a current functional programming style language. Let's try this. Here's a refrain in the modern functional program. Okay, abstractions are foundational for modular and compositional program design, and they can be layered for greater flexibility. Functions and higher order functions. Functions abstract computations or transformations over data. Higher order functions abstract patterns of computation, allowing functions to be passed as arguments or returned as results. Really? Because he's talking about Pascal here. It's interesting. He's kind of talking about two things here. I was not sure. Is he comparing procedures with functions? But let's see this. Higher order functions abstract patterns of computation, allowing functions to be passed as arguments or returned as results. It's nice, like you have values and then you have functions as values. And then you have types as values also. Parameters. Formal parameters are placeholders in function definitions that represent inputs, right? Like an A or a B. And actual parameters are the concrete arguments applied when the function is called, specializing its behavior. That's the term he uses that I haven't found in other books or like notes, like specializing. Function application. When a function is applied, formal parameters are replaced by actual arguments, and the body of the function is evaluated with those values. Data abstraction. Simple types, integer floats, structure types, lists, tuples, and user-defined types, algebraic data types. Abstractions that encapsulate complexity. Compositional design. Right. Haskell compute. Oh, that's the function compute op xy. Yeah, I like also this with Haskell. Oh, this looks nicer, right? Compute. Can we like do this? Wow. Can we do this in SML in such a brief, elegant way, like we did in Haskell? We can achieve a similar, okay, not so pretty like this, but okay. I was using a lambda here not, okay. Generic function. Fun compute op xy equals op xy. Specialization. Val sum result compute fn ab a plus b 510. Val product result compute fn ab a times b. Yeah. Okay. Let's move on. Lambda calculus. Programming languages may be characterized and compared in terms of the abstraction mechanisms they provide. Okay. Consider, for example, Pascal and BASIC. Okay. Lambda calculus. Oh, finally we come to it. After what? Hour and 23 minutes. Wow. The lambda calculus was defined. Yeah, maybe I'll stop here and do just, ML. Lambda calculus was defined by Alonzo Church in the 1930s as a model for computability and has subsequently been central to contemporary computer science. It is a very simple but very powerful language based on pure abstraction. Well, it's powerful because it kind of encapsulates this whole idea of just applying functions. Fascinating, 1930s. It can be used to formalize all aspects of programming languages and programming, and it's particularly suited for use as a machine code for functional languages and functional programming. So I guess I was wrong in saying it's like assembly. It's a machine code. Gosh, it's a machine code. It's not assembly. It's a machine code for functional languages. Isn't that crazy? That's the machine code. So do we have a machine that could run it? No, we don't. In the rest of this chapter, we're going to look at how lambda calculus expressions are written and manipulated. This may seem a bit disjointed at first. It is hard to introduce all and new topics simultaneously, and so some details will be rather sketchy to begin with. We're going to build up a set of useful functions bit by bit. The functions we introduce in this chapter to illustrate various aspects of lambda calculus will be used as building blocks in later chapters. It's important that you work through and material slowly. That's important with lambda calculus. It's really important you go slow. And maybe there appears some kind of thing after a while, like, I don't need this, or I get it. But I think what I've found out in many years that I don't get it, in the sense that you need to practice it. You, as in, to somehow get used to it, and that your mental vibe, dances with the lambdas, Okay, I'm just, this was just an expression. The lambda calculus is a system for manipulating lambda expressions. Yeah, I guess you could say like that. A lambda expression may be a name to identify an abstraction point, a function to introduce an abstraction, or a function application to specialize an abstraction. So he's basically saying that this entire thing is a lambda expression. But this entire thing can be a name, can be a function, and can be an application. I think they use abstraction. I think that's the modern way. I don't know how. I haven't seen this way. So check this out. Check this out. Lambda calculus. Wait a second. So I believe a modern way uses the term abstraction. So like there is a name, abstraction, and application in lambda calculus. Instead, I find these terms in this book. Yeah. The terms in your book are essentially an older way of describing the same fundamental ideas, but without explicitly referencing abstraction. So the modern name is name, modern equivalent variable. Yes, in some of the Lambda tutorials, you'll find the term variable, as in a name. Or bound, it can be bound or unbound. Okay, we're going to get to that. But you can say identifier, because you bind some sort of a value to something. It's called an identifier, because also it doesn't change. It's immutable. In that sense, it's an identifier. It's not something like a state, a variable. It represents a value or a placeholder in the expression, example x, y. And then function, modern equivalent abstraction. So a function is a lambda abstraction in lambda calculus, or a higher order function in functional programming. It binds a variable to an expression, creating a reusable computation. Example in lambda calculus, lambda x dot x plus 1. So this is our increment function. Example in programming, fn x plus 1. So this is, so a name, right? A name such as, well, this is 12 is a value. So it's not a name or a variable. It could be val x equals 12. Now we have a name that we can reuse. We call x, right? Or, but yes, how did we name it? Well, you can call it, I think, fun x. Yeah, this is actually a lambda expression. Lambda x dot, this would actually represent the dot x, lambda x x. And I think I would have to put that in parentheses actually. Lambda x like this, dot x. And outside we put 12 and we get a 12. This is actually the lambda expression. But we didn't name it. So in some sense you could say this is an anonymous lambda function. But we have a means of naming it, val x. Yes. And we have a function application or an abstraction, which would be fn x is x plus 1. We provided a 12, we get a 13. Or lambda x dot lambda y dot x plus y, and we provided 1 and 2. We get a 3. You see this? Okay, application. Expression, variable, abstraction, application. So this is the term that I found in most Lambda Calculus tutorials. Expression, we have a variable, abstraction, and application. So he's using, but anyway, it's not a big, it's not a sign that this is a bad book or you know something. But I think it's good also like this because it's name, function, application. And here we have variable, a name, abstraction or a function, and application. But one thing is that all of these three things are a function actually. A name is a function. So even if I give it a value 2, because everything is a function, it is a function. So in Lambda Calculus, right? If I do 12, well, it's fn x. It's an anonymous function, right? So 12. So then I get a 12. So even everything is a name, everything is a function. Not everything is an application, or maybe you could say everything is an application. Yeah. Also, isn't in Lambda Calculus, in a way, everything is an abstraction in the sense that everything is a function. You are absolutely right. In Lambda Calculus, everything can indeed be seen as an abstraction because everything is fundamentally a function. That's one of the core ideas. Even a variable like x can be thought of as a trivial function. It represents itself when applied, right? So even when you say like 2, I'm just applying it to myself and saying 2. So it's a function. It's not like you have 2, it's like you have values and then only functions when you do something, because you are doing something even when you say 2. X can be viewed as lambda y dot x, a function that ignores its argument y and always returns x. Oh, interesting. A function that ignores its argument y and always returns x. This is a constant. Wow, I kind of missed this. We'll get to this. We will get to this. Higher order functions, yeah. We did this, but this thing, oh, remind me of constants like lambda y dot x. How do we show that in SML? A constant function using an anonymous function or a named function. A constant function. Val constant is fn, no, placeholder 42. Always returns 42, ignoring its input. Wait a second. So let's say we have val constant equals fn, and this thing is like a placeholder 42. You see this? It means it can take anything. So if I call it constant, I can call it with something. Constant 2, it works, but it gives me back 42. Constant 1, 2, 1, 2, 3, it gives me always 42. Yeah, these things are really not that clear, but okay. So a name may be any sequence of non-blank characters. For example, Fred, legs 11, 19th, nervous breakdown. Okay. A lambda function, a lambda. I'm saying a lambda like Eric Meyer in his functional programming course. He's saying like a lambda, not lambda. So I'm kind of saying the same. A lambda function is an abstraction over a lambda expression. A lambda function is an abstraction over a lambda expression and has the form function, lambda name, and a body. So lambda name and a body. So that's what we were saying here actually. Val constant. Well, that was here also actually. Okay, we kind of named the entire function constant. But basically what he's saying here, it's lambda name, and the name was here just a placeholder. And the body was 42. Or maybe let's use a simple term. Val identity equals, right? So our identity function would be fn of x. X would be a name, and the body would be x also, right? So this function, identity function, gives us back whatever we give it. So lambda x, and that's it. So this is the identity function. And now we can call it identity 2, and it gives us back a 2, an int. But look at it, so the function is actually polymorphic, which means it works on any type because it's an identity function, right? It's the most, right? Look at this, identity, let's give it a string, hello world. And it gives us back a hello world with a type of string. We can even call identity, right? Identity. Type var is not generalized because of value restriction are instantiated to dummy types. Maybe I cannot. I thought I can call identity on itself. Maybe I can, but I have to provide it something. Identity 2. Let's try like this. Right. Identity 2. I wonder if SML you can do something like, do they have a pipe operator? Identity 2. Constructor, maybe not. Okay. I'll have to stop now soon. I'll continue actually practicing and maybe continue reading from next time from here. 2.5. Yeah, I'm kind of going to play with SML now a bit. Okay, wait a second. What do I do now? Yeah. All right. So this was great. I really love functional programming. All right.